the August technical presentation. And today we have Cumming from Fibre. Can I say from Fibre?
You can say Fibre. I'll correct you later.
All right. That's all right. Thanks for that. And also we have Michael and Helen from Fibre, actually Fibre, with us. Well, just a bit of introduction about today's presentation topic. As you have seen in the flyer, today will be about the use of the glass fiber reinforced polymer and its significant advantages. And our speaker, Cumming, he's a civil engineer and at the same time he's an Army officer. He's currently an executive director with the Capital Facility and Infrastructure branch of Defense. He has commanded Army engineer units on operations such as Bandar Aceh. He's played a significant role in planning the operation in the Solomon Islands. And recently Ian took leave from the Army and worked as managing contractor representative for Hansen Yongken in New South Wales, building the Sydney Harbour Wharves project. It was in this project that Ian developed an interest in aggressive environment concrete design solution based on the use of the GFRP. So without further delay, I will just pass on to you.
Thank you very much.
Thank you, Ian.
It's a pleasure for me to be here. It gives me a chance to do a bit of spruiking, but also a little bit of teaching. And I find myself in a position where you're introducing a new product into Australia as an owner of a business, and I want to be an entrepreneur, that I tend to do more teaching than I do selling. And it's more about actually getting an understanding of what's now available in the marketplace, which has actually been pretty well established for quite a number of years in other parts of the world. So GFRP has been used probably now for about 30 years, quite successfully in structural applications in the Northern Hemisphere. So bridges, concrete roads, large water facilities, aluminium plant floors, you name it, it's been built in the Northern Hemisphere. It's taken some time, however, to bring it into Australia. There's a wonderful project that sits just outside the front gate here, the Gold Coast Light Rail, where V-Rod was used. So quite exciting in that respect. There is a beginning of people seeing that there are benefits to the use of GFRP, and I'd like to go through a little bit about how it's made. Introduction to the bar, comparison with other materials, and then some of the applications. But firstly, the process, it is glass fibre. Now, whilst a fibre reinforced polymer bar can be made of a number of different fibres, including carbon and amide fibres, glass fibre tends to be probably the majority of the use that is for fibre reinforced polymer. So it's a glass, a high specification glass that's brought through a hot resin. It's then taken through, basically pulled through a dye, so you lose the voids in the material. And a lot of the quality specification about this particular bar is about the number of voids that you might find in the bar. So the more voids in it, the less quality you really have. There is a quality spec that the Canadians have. So Canadian Standards Institute, CSI, actually put out a specification for the quality of the bar. And when you purchase a bar from any one of a number of different manufacturers, you should have a look for their quality assurance program. I'll go back a step. Today, I will talk about GFRP, but there are 3 manufacturers available in Australia now, and I contend probably 4 and maybe up to 5. I was selling V-Rod along with me, so this one here made by Pultrol, which is based out of Canada. They, for the most part, do a reinforcing for concrete bar that's sand covered. You can see a copy of that there. But they also do dowels, and that's a standard dowel now that they might use in highway joins. The other one is Fibre. This one is made in Europe. It's often used, or has been used in Australia probably for a bit longer than the other 2, but really in one application only, which is the soft eye in tunnel boring machines. And the soft eye for the tunnel boring machines is quite a specific one, where you get real expertise. Most of that expertise is probably born out of Europe. It's come here, but it's also imported out a particular product. And then Mateen bar is actually one that's been alive and well in New Zealand for the last 30 years, and one that I've only just become associated with. A product that was essentially built by a farmer trying to develop a fence post that he could put his electric wires through without going out and actually creating something really much more deliberate and expensive. So a fellow called Holsworth developed this on his farm, and now he's selling that worldwide. So he's got a factory in Gisborne in New Zealand, and he also has a factory in the Middle East. And he's only just decided to bring the market to Australia, and he's quite competitive with those other two, and I'm choosing to go with this bloke from New Zealand. It's got nothing to do with my heritage, Michael. So let me go back a step. So we look at the pultrusion process. We can make a bar as long as it needs to be made within the limitations of the factory, and of course how long you might need it to be transported on. So if, for example, you needed it just down the road in Gisborne, you could make it sort of 20 metres long if you wanted to, as long as you could have the factory actually push it out that long. Most standard lengths are probably about 12 metres or 6 metres, to do with the shipping containers that you buy them in and have to transport them around the world. So there'll be a standard length. This particular process will produce, if you wanted to, a dowel. So that smooth bar that's going around now, it produces that. And in the pull-trawl process, it produces that, and then it's cut. The groove is cut post-process. So what you've got is a groove which is bound in exactly the same way as the rest of the fibres are bound to the bar, as opposed to a sand-covered bar, which goes through a process after this, whilst the bar is still hot, while the resin is still hot, and it's bonded externally. But it allows for complete gripping of the concrete matrix to the bar. So that's the V-rod. Pultron can make a sand-covered bar, but it's not the normal application. They won't do that normally. And most of the stuff that you see here, this application will produce a straight bar. The other thing that's really important to understand is it's a thermoset polymer that goes around the bar, so the resin's thermoset. So once it's manufactured, that's it. You don't put a blowtorch to it on the building site and bend it. It has to be bent in factory. That means it needs to be scheduled well and understood well by an engineer beforehand. So it might have to be shop drawn, so you've actually got those pieces of reinforcing, the bends, the cogs, the ligatures. They're all understood, they're named, they've got accurate details of what they are. You know numbers of them so they can be ordered and they arrive on the building site.
So no tack welding?
No. No. You can try. So it's made up of fibres, resins, fillers and additives, which gives, essentially the fibre gives it the strength. So the tensile strength of the bar comes from the glass fibre. As carbon has extraordinary strength that you're probably all aware of, so too glass has excellent tensile strength. We're talking probably in the order of 1,000 megapascals. So you're talking probably double the tensile strength of standard steel. You're probably talking even beyond that with stainless steel, so it's slightly less, it has less properties in that tensile realm. But it is less strong in shear strength. So where you might have, I think it's about 200 megapascals for steel, you're probably talking in the order of about 100 or lower for glass fibre in shear. So you need to treat them differently when you design. It is not a simple replacement activity from one bar to another bar. Now, I'm not a designer. I have been a civil engineer and I designed a long time ago, but I'm not a steel designer, I'm not a reinforced concrete designer. What I do know is that there are some real benefits to this, and you can test me on how to design this stuff, but I won't answer the question really well because I don't know it really well. There are some excellent guide pamphlets that I do have, and I'm more than happy to provide those to the engineers here if you want them, and I can drop them to you via email, which guides you through the process. The other important thing to understand is, of course, there's probably a decent body of evidence if you go and have a look in Google or something like that and talk about the properties of glass. You'll find that it is not happy in an alkaline environment, and concrete is generally an alkaline environment. So steel behaves reasonably well because the alkalinity protects the steel whilst ever it's not got other things that are eating the steel. In this particular case, if you put pure glass in concrete, you'd probably have issues. But the resins and the fillers and everything else protect the bar. So you've got a composite product which actually goes into making what is another composite product, which is reinforced concrete. And there is also a lot of people who will be probably detractors of this particular material that will talk just about the quality of this particular material rather than the quality of the whole of the reinforced concrete as a designed entity. And that's where I think we need to focus as the designed entity. So the composite product that is reinforced concrete rather than specifically attacking that product that might be sitting on the desk there. Because if you were to attack steel in the same way, if it sat on the desk there, and try and reverse the argument potentially, and say, for example, we've been using this for the last 100 years to reinforce concrete, and I came along as a bloke saying, look, I've got this marvellous new product. It's half the tensile properties of the one that you've got. It won't last nearly half as long, but it's a little bit cheaper. Would you buy it? Probably not. Anyway, so there's some microscopic pictures of the material, and we've already talked about some of the. I'll go back one. We talked about some of the properties. So the property of the fibres, really, because it's got such a wonderful tensile capacity, is if you go back to even Concrete 101, Concrete 101 is really the reinforcing takes the tensile load, the concrete takes the compressive load. That's probably as far back as my concrete design goes. So what you've got is a composite product that actually works well together. The trouble is, when concrete takes tension, to take tension it actually needs to crack slightly before those reinforcing elements will actually behave as tensile members within that equilibrium equation that I'm sure you're all familiar with. So there is, in some ways, this sort of perverse design methodology that's going on at the moment, which is, let's make concrete so special that it doesn't crack, so it can protect the reinforcing from actually doing its job. And you sort of, there's almost a circular argument that the concrete becomes more and more special to protect the steel in the concrete when actually you don't need to. You can actually allow these products to work well together if you wanted to in that sort of composite behaviour. So you allow it to use its strength. The other thing that's important to understand in terms of material properties, and there's some pamphlets in here that contain all of the material properties, is the modulus of elasticity, or the Young's modulus for the bar, is probably in the order of somewhere between about 53 and 65. Not 200, which is steel. So it is a less stiff bar. So that the design that you will be looking at potentially may have more cracks than you might for steel. But if you go back to what I've just said, you need to ask yourself, is it important if concrete cracks? It may be aesthetically, and your architects might get upset, but is it structurally important? And that's the key to an engineering design, is it structurally important? Because if water got into a crack with this stuff, even salt water, even hypersaline water, it doesn't matter to the rebar. Resin, transferring stresses, that sort of stuff. Again, I think I've talked about all of those things already. The other thing that's important is understanding that because it's a thermoset resin, and part of the process, as I said before, you might detail the bends and the cogs that you need before you manufacture it in factory, is those bend processes do take a little bit more effort. And if I was to say to, for example, if this is sort of a 10mm bar and say it costs $1.50 per metre or something like that, because I could probably give you a price in tonnes, but we probably prefer to do it in lineal metres. You could probably add $1 for every bend. That's how I would just pluck a figure, $1 a bend. So as an engineer, there's the opportunity to understand for your client what it means to use a GFRP design. And I would be focusing on the use of straight bar, and straight bar. Understanding, of course, that the cover that you require for this particular bar is actually right at the minimum level. So you're talking about 1.5 times the maximum aggregate size, or probably an additional 10mm over that aggregate if you're getting really close. So it can actually be very close to the surface. You can take it right up to the edge of the formwork if you wanted to, particularly if the formwork was then hidden by subsequent bits of material, subsequent building elements. You can take it right up to the edge. because the nature of the bar means that any ingress of water into it which might cause it to fail is actually highly, highly unlikely. It's a very substantial product that doesn't allow for that at all. There's some very minor amounts of that, but not to the extent that you would affect the structural integrity of the bar in the short term. And when I'm talking short term, I mean sort of decades. So here's a couple of bends. The way the bend occurs is whilst it's still warm, they turn it around whatever shape you need. So any bend that is needed will turn around 360 degrees, and then it'll be cut to achieve that. So they'll continue to run it around a spindle. So you can create a pile cage, a continuous pile cage, and then you put the straight members through it. So, for example, you might choose to do some piling work out here. You put a steel sleeve down if you wanted to. Even if it corroded away, what you could be left with is a concrete pile internal to it with reinforcing using an FRP, which has already got a cage that's catering for the bursting pressures and strains. And here's a picture of an older factory where they're using that spindle to turn the bar whilst it's still warm, and it'll cure on that, and then they'll cut it off. So you can turn it around almost any shape you like. So good specifications, good quality specs will allow us to therefore go and manufacture what's needed. There's a couple of examples there, different sizes. At the moment, we can make anything from 6-8 millimetres right through to about 38 millimetres using the pull. This one here, the Matine bar. I think there's a 42 millimetre dowel that Pull Trawl make out of Canada. I'm not sure how big Fibre look after their material, but there's a suite of different sizes that can be used. All the common diameters that you're talking about, based on sort of 1/16, so 25 millimetres, 16 millimetre bar, 12 millimetre bar, 10 millimetre bar, they're all available, easy to produce, quite attainable. So that's sand coating is one process. The other process is this one here. So as I described earlier, it's pull-truded using, basically it comes out as a bar, it then goes through a die and is cut. So that's the other method. There are also bars available made out of China where a groove is put into the bar rather than looking like that. And there are also other ones where there is, I think, a further deformation over the top of the bar, but it's not quite like that one. That's almost like a screw mechanism over it that's cut into it. Of course, that is further developed to create a bolt, what we call a Matine bolt. Pull Trawl also produce a bolt. Fibre produce a bolt, and Bluey Bar is another one that is a bolt made out of GFRP, which is made in Australia. This one's made in New Zealand. And here's some of the properties. So there's a full list of all the sorts of properties you're talking about here: flexural strength, modulus, compressive strength. Right at the top there, root diameter, outside diameter, areas, guaranteed tensile strength, and that sort of thing. So there is some basic understandings of all of those sorts of things. That is a screenshot of one of the documents that I've got in there, and I would ask, if you want those documents, can I please ask perhaps Professor Doe or someone else, just give me your email address and I'll send you all of the suite of documents that we've got about this bar. So comparison to other materials, so you're talking twice the tensile strength of steel. In terms of density, it's about 1/4 of the weight of steel. So specific gravity of steel is about 7,800. GFRP is about 2,000, 2,100. So in terms of the ease with which it's able to be used by workers, I've been on site where we've been building wharves, and the workers have said, the blokes have been doing the fixing, have said, this stuff is excellent, we love it, we can put 10 on our shoulder and walk it in, do all of that bit, walk out and get another 10. You couldn't do that with 16 millimetre bar that's 6 metres long. You'd be bringing in 3, not 10. So the workers actually find this very easy. The drawback is, of course, we don't produce mesh. So it is bar, it's not mesh. Positive of that is, though, when you're transporting mesh, you're transporting probably about 90% air, not bar. So you get one truckload of this, will probably do what a number of truckloads of mesh will do. So it saves on transport costs, but it's not necessarily that easy to produce. Now we are looking at ways that we could make it easier if there were large square metre sort of rollouts using some of the processes that are currently used at bar tied together at certain spacings. You just roll it out, then the other way, and away you go. So pultrusion down there, steel up there. This is one of the important elements of an understanding of a particular bar. So this is talking about essentially failure mechanism. So very little tensile capacity with concrete. Steel is a ductile material. It goes to its ultimate yields and remains ductile and turns into string. This particular bar is linear elastic to a brittle failure. So the way it's designed is it's not designed with a straight application of something like AS3600 because it doesn't meet some of those failure mechanisms that you're talking about. You need to design it in such a way that the American Concrete Institute or the Canadian Standards Institute demand that you do it by their standards. If you were designing it in accordance with those standards and applying some of the factors that you might do for Australia, it is a product that is easy to meet the criteria set under the BCA, where you've got an alternate solution. Now it does mean a little bit more work for an engineer, but I think in terms of the client satisfaction in particular environments, this is excellent. And of course carbon performs most like steel. It's linear elastic to a brittle failure that has a level of stiffness which is much more than glass. GFRP is fantastic in fatigue. It can go through probably another magnitude of cycles compared to steel before failure. And you can see here some of the results we're talking about here. GFRP sort of off the scale. Carbon fibre and steel just doesn't count in terms of fatigue failure. So there's some extraordinary properties that we can attest out of it. So key features, it's very resistant to corrosion because of the nature of its composite behaviour. It's electromagnetically neutral, so it doesn't conduct any electricity, it doesn't have any magnetic properties, very low density, and of course because of all of those properties, additionally it also doesn't have a very high conductivity of thermal properties and acoustic properties. It's actually quite an insulating property in many ways. Now there are some pretty good examples of where we've used FRPs. Ageing infrastructure, corrosion resistance, repairs. So, there are a couple of things that we've done recently. For example, in the corrosion resistance space, we're now building the wharves in Sydney Harbour almost exclusively out of GFRP. So all the new wharves that are being built by Roads and Maritime are almost exclusively GFRP because they actually see the benefit of it. They understand what's being built. The builder is responsible for 12 years of maintenance, which is important, and the agency wants to spend now but doesn't want to have to rebuild in 30, 40 years' time. They actually can understand that this may well give them 50, 100 to 150 years of concrete life. Now, it may well be inundated by then with sea level rise, who knows, but at least that concrete's likely to still be standing. In terms of electromagnetic neutrality, this is where I've actually seen most of the applications in Australia. So it's been put into ANSTO's facilities in Sydney. It's sitting out here in the Gold Coast Light Rail for that purpose, not the corrosion resistance, but the electromagnetic neutrality one, because it doesn't allow lead currents into a signalling area. Within ANSTO, they didn't want any steel within a particular area that they're using in there, and I can't say exactly what that is. There's a new facility being built in the University of Sydney for the nanosciences, and the electron microscopes have a need for no steel within 6 metres of the microscope, but a very substantial floor to carry the weight of the electron microscope. So consequently, they've used this. I'm just trying to think of the other applications. So there's been a number of applications overseas as well. Things like aluminium smelters, where you've got enormous currents generated that heat steel, doesn't heat GFRP, and you don't get the breaking down of the concrete from steel expanding when it's hot. So I've talked about saving in transport costs, isolation. So I'll go through some examples now, some applications. This is a parking garage where V-rod was used in Canada. There was an instant. The parking garage is perhaps the most aggressive environment in Europe. Salt, de-icing salts on the bottom of cars move into a closed-in environment that's heated. It's now hot, wet and salty, and the corrosion in the steel is enormous. There was actually one of these floors fell in, killed a bloke, and the coroner said, find me a different way of reinforcing concrete, please, and they consequently went to GFRP. There's some offshore facilities, all using concrete with GFRP. This is a harbour. There are plenty of applications where it's being used in the maritime environment. There are plenty of applications, certainly across the Middle East, but more so, probably more so in the Middle East than anywhere else at the moment. In Northern America and Canada, it tends to be the de-icing salt problem that has borne this industry. So things like crash barriers, bridges and roads have borne out the need for this. But for the Middle East, it's been places like desalination, canals, facilities right beside the sea. Here's a boat ramp that was built in, I think, Canada. This is one that was built in Australia at Wyndham. This is precast panels, top and bottom reinforcing a hole through the panel in order to lift, and they put those down straight on top of a superstructure to carry 25-tonne cranes. So it's not an insignificant, it's not a product that's just out there for little things. It can actually do serious structural engineering behaviour. This is being used in a highway in Canada. And this is sort of the guide, and I'm happy to provide this. This is something I think you can get free off the net. It's by the institution that looks after sort of new ways of doing business, the ISIS mob in Canada. And they'll probably hate me for saying mob, but they're basically a collection of scientists looking at new products and new ways of doing business. And this is their manual on design with fibre reinforced polymers. Now, fibre reinforced polymer still includes carbon, glass and amide fibres. And of course there is a need to concern yourself with carbon, because carbon does conduct very well. When you put it beside steel, sometimes you can get resultant preferential corrosion in steel. There is probably more than enough capacity as smart engineers to use glass, carbon and steel in a structure all at once, in a concrete structure. You could do a glass cage carrying a steel tensile member and maybe post-stress it with steel that's contained in tube, so it's sealed as well. So you can create a bridge beam that's actually really quite resistant to a very aggressive environment. The ACI that's relevant there, ACI 440. Again, that's one I think you have to buy off the net. I think ACI is generally reasonably keen on making sure that they make some money and continue their own processes. The Canadian one I think is about $85 off the net. Uses of GFRP, I've gone through some of them, but you can see here just tying it. Here's being tied with an electrical cable tie. This is in Sydney Harbour. This is going straight on top of. This is the first time that we used GFRP was on top of precasts with galvanised sort of cogs, and we tied it onto that. The surface, the top cast of this particular wharf is still there without cracks. Fantastic solution. You can walk all over it. You can build on it, drag stuff all over it. It's very hardy, very easy to use. It's lightweight, but you can kick it around as though you're any other builder with a bunch of steel. We've already talked about some of those things. So some of the codes, design manuals. So, are there any questions that you might have?
Does it just fix the cable tie?
You can fix it with just about anything. So a normal steel fixer will have his sort of roll of wire, and he can use that. The key is to understand what the application is, and that little bit of steel, if it corrodes, will be unlikely to actually create concrete cancer, so it's not an issue. If, however, you're doing thin facades, where you might get tea bag staining, if it were in an ocean spray area, you probably want to move away from that. If you're in an MRI room, I wouldn't be using steel anywhere, I'd be using cable ties. So it really is about the application. I'm looking forward to the day when someone can show me an automatic cable tie, because this will become very easy just to sort of shoot it with a gun and it ties it. There are automatic bar tyres, but they're reasonably expensive at the moment. Prices may come down, but we'll see.
Has there been any basic load testing on a reinforced concrete beam or research showing how the failing mode of inflection?
Look, I think we probably talk to these blokes more than me about that, but the level of scientific research is huge.
No, I just wondered if it's a basic thing, whether it's a brittle failure or whether it's a ductile one.
It will, most of the failure of a beam, the way you design it, will be about the concrete element itself failing. And the failure mechanism is most likely in the designs that we do to be a compressive zone failure. So you actually get pressing and crunching in the top of the beam, then you do a tensile failure, whether it be brittle or whether it be ductile, because that's the way that the failure mechanism is tuned into the design.
Because you're going to reinforce that using the bar there, a huge section where the bar will reach those ultimate tensile strengths.
Yeah,
right.
And you've done a bad design if that's the case. So,
well, yeah, I mean, fair enough, but we still need to understand as designers the
absolutely
way
you do.
that there's a failure in the ultimate case, because of earthquakes and things like that. So
Yeah, look, I think earthquakes would be a really good one to do some serious load testing on, because the fatigue capacity and the elasticity that you get from a bar like this, I wouldn't mind betting, and I don't know, and I would offer probably some of my own resources to allow this to occur, is to test it under a earthquake load, because I suspect, given it is elastic, more so than steel, you might actually get it moving and going back to where it was, more so than steel, which gets to a yield and then turns into string and flows everywhere, and actually is very difficult to deal with in an earthquake, particularly a collapse, a catastrophic failure of a building. And I've seen plenty of catastrophic
concrete. Normally, you don't have a catastrophic failure. You have, redistribution of loads.
Yep.
And you have a ductile failure.
Yep.
Which gives you a chance for people to come out. This sort of thing, potentially, if it is under design,
it is possible. There are places where this is most appropriate for design, and there are places where it wouldn't be. In Australia at the moment, I don't believe the appetite will be for using this in the floor designs of an internal structure for a commercial property.
Right.
It simply doesn't stack up on an economic basis for a start. And secondly, I think you're dealing with all of the issues that you've just talked about. The potential for a bad design which is not commensurate with how you should be designing for a bar like that.
Well, I certainly see the advantage of in these marine applications where you are controlling the shrinkage in the concrete, and I wonder whether the tests have been done on that. Yeah, all those sort of applications,
yep.
Even that, if it's a hydrostatic floor of some sort, that's where I see the major advantage of controlling shrinkage on long runs and in marine environments. High potential. Yeah. And or the potential for it being used. Has there been the building beam element?
So has there been a
building beam element application, and maybe not?
I think the instances where I've seen it done with a structural member for a bridge is it was done in concert with steel.
Yeah.
So they use the properties of both, and that to me is probably sensible, economically rational behaviour of an engineer to have a look at the ways that they best use the product for its best application. If I was to look at some of the roads heading south of Sydney, and that lovely big cantilever bridge that sits out just north of Wollongong. It's the backside of that bridge that is now corroding because of the sea salt spray in the mist. And it's not the big tension members, it's actually the cage of the bridge that's corroding away.
Yeah.
Why use steel in that application when this type of stuff is available? Because that would be an application where it would be applicable, and then you could use steel in those big post-tension members of the bottom.
In the early days of glass fibre, we had a lot of trouble with UV radiation and the time it took to get into the concrete and encapsulate.
Yep.
What's your situation here? Are you relying on your polymer or what are you relying on?
This particular, the Pultron Matine bar is one that's currently used right across New Zealand as a fence post for electric wires. So in terms of its capacity to receive UV rays and not break down, it's pretty good. With all of these though, I would always recommend that you store them out of sunlight, because these things do break down over time. And you're probably best off not keeping it for months out in the sunlight. You're better off storing it, containing it, covering it, and then using it, as you probably would or should with steel. Because rust doesn't help anybody, and steel should be covered until it's used.
I'm sorry, one other question. The deformations that you've got in the bar, obviously there's a desire or drive to increase the bond between the bar and the concrete.
Yep.
I guess that's the purpose of it.
Yep.
My experience on polymer coated steel application of bonds hopeless. So I just wonder whether well, you say a lot of things done, but you don't know, but
Oh, there's live testing. I mean,
bond.
this is not something that's just been produced and I'm selling it to you. This stuff has gone through decades of research. I'm just trying to remember the university that Brahim Ben Mokrani came out of in Canada. They've been testing GFRP courtesy of VROD for 3 or 4 decades. He is probably one of the world's leading lights in the material. You've got a bloke here who's tested this material. You've got people in Europe who are using this material and testing it, using it in cages, seeing how far you can do compressive strength tests with columns and with using this as the bursting reinforcing. So there has been an extraordinary amount of testing. It's not new.
No.
It's
compression testing of the bar.
Absolutely. Yeah, absolutely. So all of those functional tests have been done, and the amount of literature and research on this is extraordinary. So it's not new. In many ways, when I first sat down and started listening to people tell me about this, I asked myself, why the hell isn't it in Australia? I mean, that there are gentlemen here that say, why the hell isn't it in Australia? Well, there's probably a lot of inertia. That's probably the biggest thing, inertia, and the fact that our Australian standards committees are often influenced by industry groups as well as professional institutions as well as academics. So I think there has been a reluctance to look at the potential for this sort of problem.
And the other thing is the differential thermal expansion. It's half of what concrete is in steel. The beauty about steel and concrete, they've got the same.
The difference in that is probably marginal in terms of the effect that it has on the concrete. In terms of cracking, moving, those sorts of things, it's marginal. Again, the codes and the design codes cater for that type of behaviour. If you're talking about having a surface temperature in the order of 50 or 60 degrees, as you might in an Australian station in Sydney that's open to the elements, you're going to bury the reinforcing a bit deeper anyway. You probably would with steel. You're going to do so with GFRP.
Okay.
Except you can then put a hearing loop underneath this reinforcing and have an expectation that people are actually going to get to it rather than be interfered with by steel. So there's a number of advantages, there are a number of disadvantages. What I like to do is make sure that people don't concentrate on that product, but concentrate on what the final design element that the engineer produces is, which is the reinforced concrete element itself. It needs to be designed appropriately and it can then be used most appropriately. If you concentrate on the product, you will find fault with the product. Steel rusts. If I put it in salt water, it will last a couple of months. Put this in salt water, it doesn't. But we don't concentrate on that. We concentrate on the other bit. That's where we should be. So anyone who wants to be a detractor of GFRP, it's easy, attack GFRP. But I'm not selling it as a single system that does a job. I actually want it in a building or a road or a bridge or something like that, in which case it does a bloody good job. In most cases, particularly in aggressive environments, does a better job than STIM.
How does it fare up with acid attack like hydrogen sulfide in treatment plants and stuff like that?
It's
suitable
generally,
for application as well?
yeah, it is. It's generally very good for that. You'd have to get into some of the extraordinary numbers for acids and bases for it to start to break down the resins. But in terms of putting it in a concrete that allows for treatment facilities like water treatment and chlorination areas, and where you're doing your preparations and stuff like that, where you may have quite aggressive chemicals, there's no reason why you wouldn't use this type of material.
Following on from that, then, do they actually manufacture Fibre that does various resins and things for those purposes? Because if you go, if you look at GFRP, right, which they use in gas and that, which goes up to very high pressures.
Yep.
They basically play around with the polymers and chemical strength and the corrosion resistance. Because I think I was looking at the job and it was very specific about the resins you could use and couldn't use because of the salt.
The short answer is I don't know for sure. It is highly resistant to chemical attack as it is, and I don't know where Ultron may have gone with doing that. They've got their own, the blokes in New Zealand have their own laboratory on site, and they continuously test the glass and the resin to ensure that they're actually getting a decent product. Then they quality test the art. I don't know where they may have gone. It's probably IP that they keep protected, but I don't know. I can try and get you an answer if you wish. My suspicions are that they're probably seeking to produce a decent quality Rio bar first, making that most applicable.
Because it is the glass that breaks down polymers. So I mean, with the GFR pipes, certainly the big problem is exposing glass because it does break down. It's subject to chemical attack.
Correct. So the voids therefore allow material to ingress into it. The voids allow contact with the bit that's actually providing most of the strength and the understanding of the tensile strength of the pipes on the Rio. And if the quality of the bar doesn't allow for minimising that, you're going to get some attack. Now, there needs to be quality assurance with bar that you get, and both those two bars are well quality assured, and so is Fibre. I don't know about other manufacturers. I don't know how good they are. I just don't know. And I would hesitate to sort of place that out there anyway, to say that someone wasn't meeting a standard or not. There is a standard that should be achieved. It's actually set down by the Canadians. It's generally internationally accepted that that's what it should be. And for the most part, the big manufacturers are able to meet that with ease.
One more question, sorry, I'll shut up. Rough idea of the supply cost per tonne?
Cost per tonne.
So they implementing this into the structural rebuild of Christchurch?
I don't know. I think the guys in New Zealand are doing a pretty decent trade across New Zealand, and it is all prone to earthquakes. So it's not as if there is, I think, a resistance to the use of it in New Zealand. And the Canadians also have probably one of the most highly active areas in the world as well, down the edge of the Pacific Rim there. So they're also well aware of what seismic activities are now. I don't know of specific scientific research or engineering research that's been done on seismic capacity research, but I don't know. There may be some. I haven't done a literary research review. I make a very poor engineering student. That's it. Look,
So how are the lap lengths compared to steel? And
about the same.
about the same?
Yeah.
And is there any other connection methods?
No, really not. So there probably could be. You could probably bolt or use a form of double-ended bolt. I think there was a magnesium bolt or something like that. It was a very high-priced metal that they were looking at to do the tensile coupling of two bars. But really, the best thing to do is probably use a decent splice length. About 40D, I think, is most of it. I think steel's 40D from memory. It'll be about that. So if you're looking at a 16mm bar, you're probably looking at about 600mm to splice between the two. Yep.
I know that you need to have a flight soon, so and thanks again for coming over from Canberra just for this presentation. And we have to go back straight away. If you have more questions, I guess you can relay that through Michael. Please, Michael, if you have any question. Well, I would like to thank Ian for his presentation today, for providing us with technical information about the GFRP and especially with the appropriate application for that. And I would like to present a little gift from our regional group for your presentation. That's USB drive if you wonder what it is.
That's the best one I've ever got.
You want to remove the head. So the knowledge is here, not in the head. So
It's engineering.
all right, thank you. And I would like everyone to join me. Well, for this month, I think this is pretty much for our presentation, but we do have a few things coming up for the next month. For the presentation, we're going to have our Professor Amber Exposure, who is a mechanical engineering discipline. So we will talk about the hollow sphere structure. It's a novel material, so I guess that will be another interesting topic follow on from that one. And we're organizing a site tour of an asphalt plant with Fulton Hogan. So we're still waiting for the confirmation, but most likely that'll be on 19th of September. And again, keep an eye on your email, and I will send through the invitation. And if you look at the back, you see that our former secretary of the Gold Coast group, she's our honorary cinematographer. She's recording the presentation, and that's what we're trying to do. For this year, we're trying to record a presentation such as this, and then we will put the presentation up, the link on our Gold Coast Regional Group website. Now we're slowly uploading all the photos and material from our past presentation to our website. Once that's ready, I will send you an email saying that now we have material and recording of the presentation. If you want to go and have a look, you can do that from our website. So keep an eye on your email, don't put it on junk or spam. All right, thanks everyone, and have a good night. I'll see you next time. Thank you.